We have charges like electrons, with a force which is enormous.
Hi there, welcome to the Electronics channel. Power factor correction involves modifying a circuit in a way that increases the power factor, and ideally you want to increase that power factor to 1. Power factor, by definition, is the ratio of the real power delivered to the load divided by the apparent power in the system. And apparent power in the system is equal to VRMS times IRMS. And it turns out that the closer the voltage and current are in phase to each other, the closer to 1 your power factor is going to be. Because if your current and voltage are in phase, then your S and your P are going to be the same. And power factor correction involves converting a circuit where the voltage and the current are not in phase with each other to a circuit where the voltage and current are closer to in phase with each other. And if they're perfectly in phase, then your power factor will be 1, and that is the ideal situation. There are actually 2 parts to power factor. The first part is called the displacement power factor, and that displacement power factor is due to reactive loads like this inductor in the circuit here. And that inductor in the circuit there is going to displace the current with respect to the voltage. The current's going to be out of phase with the voltage. The second part of power factor is called the distortion factor, and that's due to harmonics in the voltage or the current in the system. And for example, that will happen when your voltage is sinusoidal, but maybe your current, because of nonlinear components in the system, is not sinusoidal. This video is going to focus solely on the displacement power factor. So if your displacement power factor is less than 1, what do you do to the system? What kind of components can you add to the system to improve the power factor and push it closer to 1? To start with, let's take a look at why power factor correction is important. Why do we care about improving the power factor to 1? Well, let's take a look at a system that's rated to carry 100 amps at 480 volts. So in this case, this system is going to be rated at 480 times 100, or 48 kVA, 48,000 VA. It doesn't matter whether the voltage and current are in phase or not. The rating is always going to be the RMS voltage times the RMS current, and in this case it's 48 kVA. So in system 1, power factor correction is applied. So system 1 has a 480 volt source, and in this system the power is 40 kilowatts and the power factor is 0.95. It's a 480 volt source. And so this is telling me, this power of 40 kilowatts and the power factor of 0.95 is telling me that the apparent power being delivered to the system is 40 kilowatts divided by 0.95, which equals 42.1 kVA. So in this system, the apparent power is less than what is rated for, so this system's going to work. And in this particular case, the RMS current, because the apparent power is 42.1 kVA, I can figure out what the RMS current is going to be. 42.1 kVA divided by the 480 volts, and that gives me a current of 83 amps. So this 83 amps is going to the load driven by the 480 volt source and keeping the apparent power under the rated power. A second system that does not have power factor correction has a block where the power is still 40 kilowatts. The power that's doing the real work is the same as the system with PFC, but in this case the power factor is 0.8, still coming from this 480 volt source. In this case, the apparent power is still 40 kilowatts, but this time divided by 0.8, and that gives me 50 kVA. So even though the same amount of real work is being done, because my power factor is too low, the apparent power exceeds what it's rated for. So this system is not going to safely operate. If I want to know what the current is, the current in this case is, using that same equation as I did with system 1, the current is 104 amps RMS. So you can see that that higher apparent power is also resulting in a higher amount of current being driven to the circuit. That higher current may be the reason that this particular system is not going to work. Maybe the wires in the system are not rated to carry 104 amps, but you need that 104 amps in order to get the 40 kilowatts delivered to the load. So by adding this power factor correction, you're able to have a system that delivers the 40 kilowatts and keeps the apparent power under the rated requirement. At its most basic, power factor correction involves adding a reactive load to counteract the reactive load in the circuit. So in this circuit over here, the inductor is the reactive load, so the power factor is going to be fairly low, but I can introduce power factor correction by adding this capacitor, which will counteract the reactive power of this inductor. So for example, let's say that the resistor in this load consumes 10 kilowatts of power and the inductor is 9 kVAR. That means my apparent power is going to be the square root of 10 squared plus 9 squared equals 13.45 kVA, which gives me a power factor of 0.75. 10 kilowatts over 13.45 kVA gives me 0.75 power factor. Now if I introduce the capacitor here, and that capacitor has the same amount of reactive power as the inductor, 9 kVAR, my apparent power is going to be equal to the square root of 10 squared plus 9 minus 9 squared. The 9 kVAR of the inductor and the 9 kVAR of the capacitor cancel each other out, and I end up with square root of 10 squared, which is simply 10 kVA. And since my apparent power and my real power are equal to each other, my power factor is going to be equal to 1. That's kind of as straightforward as it gets. The only additional calculation you would need to do is for that particular circuit, what is the actual capacitance value that I would have to add in to counteract the 9 kVAR of inductive power. So that previous example that I looked at was really easy because I knew the reactive power of the load, so I just have to counteract that with the reactive power that I add to the circuit. But capacitors and inductors are, of course, not rated that way. The reactive power is going to depend on the reactance, which depends on frequency. So when doing a paper analysis to determine the compensation value, the component value that you're going to need for power factor correction, you need to take the component values and the frequency values into consideration. So let's take a look at this example here and figure out how I would correct for the low power factor of this system. First thing I want to figure out is what is the power factor of this particular circuit, and then what capacitor value I would put into this circuit to get a power factor of 1. All right, let's start off with looking at that inductor. The inductor is 10.6 millihenry, therefore it has a reactance of 2 pi times 60 hertz times 10.6 millihenries, and that works out to 4 ohms. The next thing I can look at is the total impedance of this circuit. In rectangular coordinates, that's easy. It's 3 plus j4 ohms, or 5 ohms with a phase angle of 53.13 degrees. The current in this circuit is going to be 480 volts, and that's 480 with a phase angle of 0, divided by this total impedance that I just calculated, and that works out to 96 amps with a phase angle of minus 53.13 degrees. The apparent power doesn't care about the phase angle, I just need to know what those RMS values for voltage and current are. So the RMS voltage is 480 volts, the RMS current is 96 amps, and that works out to 46.08 kVA. The real power consumed by that resistor is equal to the current through it squared times the resistance of 3 ohms, and that works out to 27.65 kilowatts. Combine those two numbers together to get the power factor, P over S. So 27.65 divided by 46.08 gives me a power factor of 0.6. 0.6 is pretty low. So what am I going to do to correct for that 0.6? Well, in general terms, as we saw in that previous example, I can add a capacitor here. And that capacitor is going to have some kind of reactive power associated with it. And it is the opposite type of reactive power as the inductor. So if I can match those two reactive powers, I can get my power factor up to 1. I don't know what the reactive power of that inductor is, so I need to figure it out. The reactive power of that inductor, that's pretty easy to figure out. That is the current through it squared times the reactance of the inductor, and that works out to 36,864 var. So I need QC equal to QL. And I am putting this inductor in parallel with my source. And the reason that I'm doing that, well, a couple of reasons. In practical terms, it's going to be easy if you are an operator sitting at the source of your system. It's easy to add a capacitor there in parallel with your load. You don't have to break the circuit to add anything in. It's just switch it in or switch it out. In terms of calculations, it's also easy to figure out what capacitance you need to put in there because you know the voltage across the capacitance. And knowing the voltage across the capacitance allows us to easily figure out the reactance of that capacitor, because one equation for the reactance of the capacitor is the voltage across the capacitor divided by the reactance of the capacitor. I know the voltage across the capacitor is that 480 volt source. I know what reactive power value I need. The only thing I don't know in this equation is my XC, the reactance of that capacitor. XC is going to be 480 squared divided by 36,864 var. Plug those numbers into my calculator and I figure out that I need a capacitor with a reactance of 6.25 ohms. That, of course, is frequency dependent. So what is the actual capacitance value that I need to add into here? Remember, XC is equal to 1 over omega C, which means the capacitance is equal to 1 over omega XC. Omega, of course, is 2 pi times 60. The XC that I need is the 6.25 ohms. Plug numbers into the calculator and I get a value of 424.4 microfarads. So if I could add a capacitor with a value of 424.4 microfarads, the reactive power that it consumes is going to match the reactive power that the inductor consumes, and they're basically balancing each other out. Therefore, my circuit will only actually be consuming real power. I don't have any net reactive power that I'm putting into the circuit. Since there's no reactive power, my power factor, which is the real power divided by the apparent power, is going to be equal to 1. And I have fully corrected the power factor, brought it to its maximum of 1, and my circuit will live happily ever after. So that gives you the tools to compensate for a low power factor when you're only dealing with displacement power factor. Thanks very much for watching. I'll see you in the next video.
If the mouse is brought into one of the squares, it closes the appropriate reed switch. This gives a signal to the electromagnet to move over to a position underneath that square.
With a force which is enormous.